Last week, we were looking at the properties of tensors. We began by looking at the fact that properties are built on the foundation of the definitions. So if you want to examine any property, you go back to the definition, and then you get all those attributes. Those attributes are coming from the definitions. We talked about equality, what equality means. We talked about multiplication by a scalar, and then the inverse, and we showed that the inverse of a tensor is also a tensor. We showed that when y is the inverse of t, t is also the inverse of y. And the product, no matter how you arrange it, is that ty or yt will be equal to the identity tensor. And then, what did we do? We looked at the components, the tensor basis. We know that just like you have your vectors having E1, E2, E3 as bases, once you are dealing with tensors, you have 9 bases. That would be E1, 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 E2, E1, E3, E2, E1, E2, 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 E3, E3, E1, E3, E2, E3, E3, and all of them with the tensor product between those basis vectors. There are 9 components of a tensor, and those 9 components can easily be found. So the 9 components can be found from this expression here. So just let I and j take all the values of 1 to 3, and you get 9 equations there. This is actually not just one equation, but 9 equations. We were therefore able to find the components of special tensors like the identity tensor, the spherical tensor, the annihilator tensor, and the dyad. Then we were able to talk about products. And then we specialized on the composition. It's a particular kind of product, which we defined. And then we looked at how to get composition of dyads, composition of dyad bases. And from there, we looked at how to get the components of the composition. And then we looked at a rule for chaining dyads. So you have several dyads in composition. You only need to worry about the first and the last dyad. You take the first and the last dyad, and you take a dyad based on the beginning vector and the end vector. And then all the near vectors are multiplied in dot products. And because of that, we were able to not only define the transpose, we were able to find the component of the transpose in terms of the original components. In many books, we use this to define the transpose, but our definition of the transpose is more fundamental because you can derive this rule from our fundamental definition. And symmetry comes when a tensor is indistinguishable from its transpose. When its tensor and its transpose are the same, then we say that that kind of tensor is symmetrical. If a tensor has an inverse, not all tensors that have inverses, if you can find the inverse of a tensor, you say that that particular tensor is invertible. If you cannot find the inverse, then the tensor is not invertible. Now, we begin on this page, and we are now discussing the cofactor of a tensor. The cofactor. We have talked about the transpose, the inverse, and we talked about symmetry. Now we are talking about the cofactor. To get the cofactor of a tensor, you have to do 3 things. You first of all have to take the determinant of the tensor, which we will define in this class. What is the determinant of a tensor? We will define that. And then you take the inverse of the tensor and transpose it. So this t raised to the power minus t is the transpose of the inverse of t. So it's a complicated process. Get the cofactor of a tensor, you take the transpose of the inverse of the tensor, and you multiply that result by the determinant of the tensor. Once you do all of that, you get a tensor called the transpose and the cofactor of the tensor. That cofactor turns out to be a very important tensor for physical applications. Very important. So by t raised to the power minus t, we invert and transpose the result. We will later define the cofactor in a way that does not presuppose that the tensor is invertible. The fact that the tensor is not invertible does not mean it cannot have a cofactor. So we will define that later. You don't want to introduce that definition at this point, so as to be focused on the simple matters we want to discuss today. This definition looks quite big. However, don't be faint-hearted. There is a physical interpretation that makes the knowledge not only worthwhile, but compelling. Determinant of t, determinant of a tensor is really defined, as we shall see. Now, is the cofactor itself a tensor? The cofactor of a tensor, is it of its own a tensor? Can you prove it? Let me see whether there's anybody who wants to answer that question. Class, chat room, everybody, chat room. Yes, there are two questions on the board. Is the cofactor, as we have defined it, is it a tensor? We have just defined the cofactor, and that definition is on the board. Is a cofactor a tensor? Some people have said it's a tensor. So, Israel Olaoye does just thinks. Jenica Odua says it is. Now, the second part, can you prove it is? It is a tensor. Can you prove it is? Can you prove it? Well, to prove that it's a tensor is very easy. First of all, remember that determinant of a tensor is a scalar quantity. So if we are multiplying something by a scalar, so multiplication by a scalar does not change the tensor attribute. So forget about the determinant of t here. Now, remember that t inverse, let me write this in another way. I can say this is equal to, okay. So if we look at this expression here, we'll see that this is the transpose, is the invert. You invert the tensor first, and then you take the transpose. So that's what we mean by this. Now, is the transpose of a tensor? Okay, so the transpose of a tensor is a tensor. So is the inverse of a tensor? So if the inverse is a tensor and the transpose is a tensor, performing those two operations cannot change the tensor nature, because the inverse of a tensor is a tensor, the transpose of a tensor is a tensor. So if we invert and transpose, we are still having a tensor. So that is so the cofactor of a tensor is also a tensor. In order to motivate today's lecture, the main point of today's lecture, which is the invariance of a tensor. What we are really concentrating on today are the scalar invariants of a tensor. We want to begin from familiar grounds. Let us talk about scalar functions of vectors, and let us see how much of it you remember. I want to see how much of it you are scared about, and I would hope that I will dispel those fears or scares right away. So, are there scalar functions of vectors? Are there scalar functions of vectors? Are there scalar functions of vectors? That question can be posed in a more elementary way. If I supply you with a vector v, how many scalar functions can you compute from that given vector? Before you answer that question, what does it mean if I supply you with a vector V? What does that statement pose? What does it mean if I supply you with a vector V? Tell me any way you know that I can supply you with a vector V. 3, sir. What does it mean by 3? What do you mean by 3? Oluwatobi. Olajide. Okay, I'll give you 3 scalar functions. Okay, if I give you 3 numbers, those are the components of the vector. If I can give you the X component, the Y component, and the Z component, I've supplied you with a vector. Correct. Is there any other way I can supply you with a vector? Is there any other way I can supply you with a vector V? Is there any other way? Somebody has said I can supply the 3 scalar functions, 3 scalar components. What other thing can I do to supply you with a vector V? Anybody? How else can I supply you with a vector V? Okay, if I supply you with a magnitude and I supply you with a direction, and I say that is the magnitude of the vector and the other one is the direction, then that means that I've supplied you. Okay, Oluwapelumi is now saying it after I've said it to provide a set of values that have magnitude, not a set of values, just one magnitude and one direction, not a set. If you want to supply me with a vector V, you supply me a particular magnitude and a particular direction, not a set. So you are still wrong, Oluwapelumi, even though you are pirating me. Okay, so if I supply you with a vector, the magnitude and the direction of the vector. Once I supply those two, and you can draw the magnitude as the length of a line and the direction of the line. You know everything you need to know about the vector. Okay, good. So if I supply you with a vector, how many scalar functions can you compute from that given vector? How many, or put it another way, how many scalar by nature can you compute from that given vector? Jenica said 1. Does everybody agree there is only one thing we can compute that is scalar from that vector? Oreoluwa agrees. Chigozie Nadi agrees. David Anigbo agrees. Philomena Oze Ezilo agrees. Oluwapelumi Joseph says there are 3. Oh, so Oluwapelumi is the first person to disagree. Oluwapelumi is the person who is more correct. The others are completely wrong. That's everybody saying 1. There's only one scalar you can compute is wrong. The person who says there are 3 is closer, but still not correct. Well, let me just say there is at least, I can compute at least 5 scalars. Because given the vector, I can say, okay, the X coordinate, which is a scalar quantity, and is coming from that vector. And the Y coordinate is another scalar quantity, and is coming from that vector. The Z coordinate is still another scalar coming from that vector. The magnitude is still another scalar coming from that vector. The direction is still another scalar coming from that vector. The square of the magnitude is still another scalar coming from that vector. In fact, there are infinitely many scalars that we can compute from that vector. They may not all be independent, but they are different scalars that we can compute. So there are at least 6 or 100 or 10,000 that you can compute. Those are all scalars based on the vector. So there are many scalar functions that can be found from a vector. If there's anything scalar whose value can be found, once we know the vector, once the vector V is fully defined, we can call that thing from the math we know so far a scalar function of that particular vector. For instance, that means that the X component is a scalar function of that vector. The Y component is another scalar function of that vector. The Z component is still yet another scalar function of that vector. The magnitude is another scalar function of that vector. The square of the magnitude. So I just want you to see that when we talk about scalar functions, there are plenty of them. So So there's no shortage of which one, so we can only choose which one we want to use, but there is no problem getting them. There are many scalar functions. I just want to focus on some scalar functions that you might have been afraid of, but I want to dispel your fear. For instance, the direction cosines of a vector can be defined easily. I take my v in this particular case to be on the xy plane, but it doesn't have to be. As long as you can just take the angle alpha 1, alpha 2, and alpha 3 to be the angles made to the x, y, and z axis. All we are saying here would still be valid. And if v1, v2, and v3 are the components of the vector in the 3 coordinate directions, maybe initially we can let v3 be 0, but it doesn't have to be. Whether it's 0 doesn't matter. So clearly, alpha 1 is the angle whose cosine is v1 over the square root of v1 squared plus v2 squared plus v3 squared. If v3 is 0, then it's just the square root of v1 squared plus v2 squared, as it is in the diagram that I've drawn here. Doesn't matter. That is the first direction cosine. The second direction cosine is the angle whose cosine is v2, where v2 is the projection on the second axis of v1 squared plus v2 squared plus v3 squared. The third direction cosine is alpha 3, which will be the angle whose cosine is v3 over the square root of v1 squared plus v2 squared plus v3 squared. Before we even go to the test mathematical form, if v3 is 0, can somebody tell me what alpha 3 will be? If v3 is 0, what will alpha 3 be? Yes, Kamai Adebayo and Ginika Olua are correct. One expresses the answer in radians, the other one expresses it in degrees. So you can see that the rest of you that answered first were wrong. All the people writing 1, 1, 1 are wrong. And if v3 is 0, then the third direction cosine is 90 degrees or pi over 2 if you measure it in radians. So that is, okay. So can everybody agree with me that this alpha 1, alpha 2, alpha 3 can be written in the mathematical form as alpha I is equal to the angle whose cosine is v dot ei over the square root of v dot v? Can we all agree? Do I have agreement there? Is it accepted? Okay, so you can see, so it is possible. Okay, so if therefore you look at this formula, you can see that everything we need is here. We know the vector v, therefore we can take its dot product with the coordinates, and then we can take v dot v, which will be a scalar. V dot v will give it, the dot product of v with itself will give us a scalar, therefore we can take the square root of a scalar. So that is it. So you can see that these direction cosines are all scalar functions of the vector, because they are functions of the vector, because once you know the vector, you can compute any direction cosine you want. So if you are afraid of the word direction cosine, there's nothing more to it than this. So piece of cake. So given any vector, there are 3 scalars such that once you specify a coordinate system that can be calculated. And sorry, once you given any vector, there are 3 scalars such that once you specify a coordinate system that can be calculated, those 3 scalars can be calculated, which you specify in coordinate system. These are scalars that depend on the vector as well as the given coordinate system. Symbolically, we can say that the function depends on the vector v and the coordinate system. Let us G to symbolically represent the coordinate system. So each function is dependent on v and g, and we call it alpha I, which is the direction cosine. Where the scalar alpha I depends on both the given vector and the given coordinate reference. G is defined by the base vector. So the coordinate reference is defined by its base vector. So instead of G here, we could have put E1, E2, E3, which are the things that specify the, if you are looking at orthonormal Cartesian basis, that's the base. So Fi depends on V. So on E1, E2, E3. So we can have scalar function. Now, this scalar function, let us look at other scalar functions. Given any vector, there are still scalars. Once you can calculate, you've already seen that. Okay, we've already talked about that. So, are there other scalar functions? Yes, there are. For instance, the dot product of the vector with itself is a scalar. Therefore, which depends on the vector. So it's a scalar. Even its square root or even its square, all those ones scalars. Now, I have another question for the class. Let me type my questions so that is there a fundamental difference between these scalar functions and the direction cosines? Is there a fundamental difference? Is there something that distinguishes these new ones, this v dot v or the square root of v dot v, compared to the direction cosine we were discussing? Is there a fundamental difference? If there is, what is it? Let us know that they are all scalar functions. But is there something about these ones that's different from the other one? I want to see whether anybody can see something fundamentally different. There is a difference. What is the difference? Kamal, Ibini Jesu, what's the difference in the nature of those two classes of functions? There's another thinker here. Oluwapelumi is a thinker. He thinks, doesn't know, but he thinks. Okay, it's good. I like thinkers. I like those who can think. And what is the difference? Now we have gone to the second round. Now, what is the difference? What? Ajibola says there is no difference. Well, Ajibola, you are wrong. There's a difference we want to discuss. Any difference? What is the difference? Well, you see, in the direction cosines, okay, let me see, the scalar functions are mathematical functions, scalar input map. No, that's not no. You are trying, but you are not, no. You see, can't you see that these other functions are dependent only on V? This one depends on V and G. It depends on V, but V alone cannot give you the direction cosines. You also have to specify the coordinate system you are using. But when you are talking of the magnitude of a vector, for instance, it depends on the vector itself, the vector only, and nothing else but the vector. It doesn't matter what, it does not matter if I tell you the velocity of a car is so and so and so. You can't tell me to which Cartesian coordinates. Whether the car doesn't even know there's anything called Cartesian coordinates. You can take any coordinates you like. If I take one coordinate system and you take another coordinate system and we both calculate the velocity of that vehicle, we are going to get the same scalar answer. Our answers are independent of what orientation or whatever we choose. Because of that, we can say that the magnitude of a vector is an invariant because it's an intrinsic property of that vector. It doesn't care what Cartesian coordinates you are taking. It doesn't know whether you are taking coordinates or not. It is an intrinsic thing. So because of the intrinsic nature of the magnitude, we can say it is a scalar invariant. It is not just a scalar function, but it's a scalar invariant. So I want you to see that given a vector, we can define scalars, and those are scalar functions. But scalar function pass scalar function. Not all scalar functions are created equal. There are scalar functions that need extra information for computation. But there are scalar functions that do not need any other thing for computation, and they are invariants. They are invariant because their value does change and they do not need. There are two things that make them invariant. One, their values are always the same. Two, they do not require any other piece of information for computation. Don't need to use any other piece of information. You compute them straight, and that's it. Okay, so now let me ask another question. Why is x coordinate of a vector not an invariant? Or y coordinate or z coordinate? Why are those coordinates not invariants? Why are the direction cosines not invariant? Because they depend on the basis vector that you are using. So if you choose another basis vector, not basic, it's basis. The vectors that form the base, the BASIS, the basis vectors that you are using, the vectors that form the base. And they don't remain constant. If you change coordinates, you get new values. Unlike the magnitude, if you change coordinates, you still get the same value. So they are invariants. The magnitude of a vector is independent of its of the direction of the way you are orienting your coordinate system. So you can see the difference between scalar functions and scalar invariants. So you agree with me that a scalar function is slightly different from a scalar invariant. A scalar invariant is still a scalar function, but it has an invariance in it. That is, it does not change with other factors. It only depends on the vector. So we are going to move from here now. We are going to move to tensors, and we are going to discuss invariants. So you must keep in your mind, when we say something is an invariant, we are saying it depends only on the argument. It does not depend on external factors. It doesn't depend on anything else. So if I say this is a tensor invariant, I'm saying it's only a function of that tensor depending on nothing else. If it is like that, it is now a vector invariant. So we are looking at invariants, which are scalar functions of tensors that do not vary. So in order for us to go into this study, it's a big subject on its own. It is a big subject, but there is part of it that is of interest to us from an engineering standpoint. Certain functions of a tensor are often more the primary interest of the engineer than the tensors themselves. So the engineer is more interested in some functions of tensor than even the tensor itself. So what the engineer is looking at is not the tensor, but some functions. Examples include in mechanical design, you are looking at the von Mises or equivalent stress or equivalent strain. All these are not the stress tensor itself, but it's a scalar function of the stress tensor or a scalar function of the strain tensor. In deformation analysis, you are interested in the dilatation or the magnification ratio or the volume ratio. Again, all of these are scalar functions of the tensor. In vibrations and control, you are interested in natural frequencies, mode shapes. All of these are scalar functions of the tensor, not the tensor itself. So there are scalar valued functions like equivalent von Mises stress, equivalent strain, dilatation, volume ratio, natural frequencies. All those ones are scalar valued function of tensors. There are vector valued function of tensors, mode shapes, principal planes. They are functions of tensors. They are actually functions of the stress tensor, which we will talk about at another time. Mode shapes or vibration results, they are vector valued. There are also tensor valued functions, the area magnification, the reference map. All these ones are tensor valued. So a function of a tensor can be scalar valued, it can be vector valued, it can also be tensor valued. But today, we are looking at scalar valued invariants. So we are looking at functions that have two qualities. First of all, they are scalar functions of the tensor. So the fact that you have a tensor doesn't mean you cannot produce a scalar out of it. You can produce a scalar out of the tensor. So this function itself is scalar valued. But it is also invariant. Doesn't depend on any other thing apart from the tensor. So when you have something that is scalar valued and completely dependent of other considerations apart from the tensor, you call it a principal invariant, and it is principal scalar function of the tensor. So we are studying today invariants of tensors, invariants. And we are looking at what is usually called principal invariants. The reason why we are talking of principal invariants is that there are other invariants that are not principal. We are not, so there are, these particular invariants are the ones that are mostly used, and they are called principal invariants. It is not, they are not the only invariants you can form. It will be possible to formulate other invariants, but these ones are called principal invariants. They are principal invariants and they are scalar valued. They are scalar valued. So they are scalar functions of tensors that are invariant, that are called principal invariants. That is the main purpose of today's class. We deliberately didn't dabble into this last class because I wanted you to concentrate on the issues that we are talking about without confusing them with the new issues of the scalar invariants. The scalar invariants are so important that they are going to be taken in a class of their own. If we don't finish, we might even spend another lecture on it. It's really important. There are 3 of them. Before we define them, please take note. Given 3 linearly independent vectors, A, B, C, remember that the scalar triple product A dot B cross C can be written in a compact form as A, B, C, and before I go on, I'm going to ask you, why is it possible to just write it as A, B, C, Why is it possible? Why do we write it like this instead of putting the dot and the cross? Why are we doing that? Why is it okay to just, instead of writing A dot B cross C, why is it okay to just say A, B, C? Yes, even just you are right, we are getting compactness, but why is it? Does it matter where the dot and the cross is? Does it mean that it doesn't matter where the cross and the dots are? Why would we just say, no, it's not because no. David and Igbo, you are wrong. Ibn Jesu is right. The thing is that A dot B comma C, and so A dot B cross C and A cross B dot C give you the same result because it doesn't matter. That's why you can just ignore dot and cross and just compactly write it as A comma B comma C, because the orientation, the location of the cross can be interchanged with the dot without any penalty. You must remember that when because of that, we can write it in this compact form. So just notice that. Therefore, we're going to now define the three invariants that are of concern to us as shown. The first one is called the trace of T. Trace of T, all of them are divided by A, B, C. So I will just be talking about what is on top, since what is at the bottom is given and known. Is A, B, C, A, B, C, A, B, C. So I'm concentrating on what is on top. In what is on top, there are 3 brackets. The first one has the function operating on A, leaving the remaining. The second one has the function of the vector and the tensor operating on B. And then in third bracket, it has the tensor operating on C. If you have these 3 divided by A, B, C, what you get is defined. It is defined as the trace of T, and it is a scalar function. It's a scalar. Why is it a scalar? Because everything in every bracket here, they are all scalars. This is a scalar, this is a scalar, this is a scalar, divided by a scalar. Scalar divided by a scalar will give you a scalar, because everything, don't forget that T operating on A will give us a vector. So it is a vector scalar product. A T operating on B will give us another vector. This is a vector scalar product. And then operating on C will also give us a vector. So this is a triple scalar product. So it's a scalar. So it is called the trace of T. The second invariant, if you look at the way we did the first one, the second one should be easy for you to see. Instead of operating T on only one, we take them 2 by 2. We operate T on A and B, here on B and C, and here on C and A. So the logic is almost the same. So these two formulas, once you can remember one, you should be able to remember the other one because it's just so easy. In the third one, you operate T on each of the 3 vectors. And the answer and the result you get is called the determinant of T. This is the definition of the determinant. This is the definition of the trace of the cofactor. And this is the definition of the trace. So those are the 3 principal invariants. There are 3 principal scalar invariants. And the interesting thing about it is that all of these 3 are completely independent of whatever vectors you choose as A or B or C. It doesn't matter. It does not matter. Just choose any set of linearly independent vectors. The reason, okay, why must the vectors be linearly independent? Class, go to the chat room. Why must the vectors be linearly independent? Why must A, B, and C be linearly independent? Why must A, B, and C be linearly independent? Because we say A, B, and C must be linearly independent, but once they are linearly independent, these functions are completely independent of them. But why must A, B, and C be linearly independent? So that they can form a basis. Well, you are correct. So that they don't give a division by 0. It's not that it's, you are almost right. What is his name? Oluwatobi Aliu. It is not so that it's because, you know, if they are not linear independence, A, B, C will become 0. So you are now going to be dividing by 0. It is to avoid the division by here. So that's why they must be linearly independent. If they are not linearly independent, you have the jeopardy of your being divided by 0. And once you divide by 0, you get a NaN. NaN in your village, that may be a baby formula that you give to little children, but NaN here means not a number. You get a NaN, and the NaN here is not nutritious at all. It's can cause constipation. It's not a number. So you get a NaN that can cause constipation, and we do not want to get a NaN that can cause constipation.